The next topic is discriminant analysis. So with discriminant analysis, again, we're trying to predict some labels for variable y, which is a categorical variable or a discrete variable. But now, instead of using logistic regression, we're using discriminant analysis. So discriminant analysis is kind of a general method. Today, we're going to talk about linear discriminant analysis, quadratic discriminant analysis, and naive Bayes. So all these three methods, they start with the Bayes theorem. So Bayes theorem says that probability of y being equal to k, given x is x, this is some instance, we can use the Bayes theorem to flip things around. So we write it as probability of x being equal to x, given y is k, times the prior, which is just the general probability of y being k, over probability of x, probability of x being x. So this is Bayes theorem, right? Usually we need to expand the denominator because probability of x being x depends on the classes. So let me first give you an idea about what's going on here. So we want to predict whether we want to predict the probability that a fish is salmon and not a tuna, right? So the data set that we have is this, right? We have some x1, some x2, and some y, and we want to estimate the probability that some fish is a certain type, for example, salmon, given that its length is 3 meters. So what we're going to do is checking how common it is for a salmon to be 3 meters. So here is the distribution of length of salmon, and here is the distribution of length of tuna. Tuna is generally longer. So these are salmons, and these are tuna. And this is length of fish, which is x1. And here we have the density, probability density. Where does the probability density come from? Well, we have been in the in fishing business for some time, so we have historical data, and based on the previous fish that we have caught, we know that the histogram of length of salmon looks like this. We just have the histogram. This is salmon. And for tuna, the histogram looks like this. This means that we cannot say with certainty that every single tuna is larger than every single salmon, but generally, from our experience, we know that tuna fish is just more likely to be longer and I guess heavier. So from this historical data, which is about length of fish and their type, and here on the y-axis we have the frequency, right? We just checked, in our historical data, and we learned that in the past 100 days we have caught 2 fish which were, I don't know, let's say 40 centimeters, and they were both salmon. So this is 2. And we caught 4 fish where the length was between, let's say, 40 to 50, and they were salmon. But we don't have such tiny fish for tuna, right? So the smaller tuna that we caught was 100 centimeters maybe, right? And let's say, I guess tuna could be maybe up to 4 or 5 meters. So 500 centimeters, right? Maybe salmon, I guess to be more realistic, I guess there's also 2-meter salmon. So from this historical data, we have these 2 probability densities. So now with Bayes' rule, what we're doing is, in order to check whether a certain fish is salmon or tuna, we flip things around using Bayes' theorem and say, all right, among the previous fish we caught, which were salmon, how many of them had this length, x? Or how many of them, let's say, were 100 centimeters? So 100 centimeter is here. And we just look at the probabilities. This is the probability density of tuna being 100 centimeters, and this is the probability of a salmon being 100 centimeters. While both of them are possible, it's much more likely for a salmon to be 100 centimeters compared to a tuna, because in the distribution of tuna, 100 centimeters is quite an unlikely event, but for salmon, it's more likely. So Bayes' theorem says that we can calculate the probabilities by using this in the numerator, right? So in the numerator, we have this, times the prior. So prior is just, just the probability of a class regardless of input. So let's say we are fishing in Canada where salmons are twice as many as tuna. Just generally in this kind of ecosystem, there are twice as many salmons as tuna. Therefore, this will be 2/3, right? For salmon, this will be 2/3. For tuna, 1/3. Yeah, and then for the denominator, we're going to kind of use a combination of these so that the result will be some probability. So that's discriminant analysis. That's it. So discriminant analysis uses Bayes' theorem and looks at how common a certain input value is for a given class. Then there are like 3 flavors of implementing this idea. One type is LDA. This is when we use normal distribution for this. So we have histograms. These are not distributions, right? We need to fit a distribution here. One idea is to fit normal distribution. With LDA, we're going to fit normal distributions with the same variance. So when you have 2 normal distributions with the same variance, they're going to be their height are going to be the same, because when the variance kind of defines how, variance kind of defines this. And as the likelihood, the area under the curve should be 1, you cannot make them taller when the variance is the same. So with LDA, we are using, let's say, 2 bills of the same height. That's LDA. And as they have the same height, there will be a lot of cancellations in some mathematical equations just because of this nice kind of geometry. That's LDA. Then we have QDA, which says we use normal distributions, but they don't have to have the same variance. So we can use one normal distribution with a low variance, maybe for salmon, because salmon just has lower variation of length. But for tuna can be maybe something like this. So this gives us QDA. So QDA uses normal distributions with different variance and therefore different heights. Now we don't have those kind of nice geometric properties that allows us to do some simplifications in the model. Therefore, we get a more complicated model. We get a more complicated model, which is going to be quadratic. That's where Q comes from. This one, initially the model might be quadratic, but then the quadratic terms kind of cancel out with each other, and we get linear. This is linear discriminant analysis. This is quadratic discriminant analysis. And then a third idea is naïve Bayes. So with naïve Bayes, again, we are kind of, with naïve Bayes, we're assuming, actually I cannot really visualize it. With naïve Bayes, what we're doing is, we're assuming conditional independence. We assume conditional independence between variables, for example, between x1 and x2, which is quite a strong assumption. For example, x1 is length of a fish, x2 is weight of a fish. And I think it's pretty clear that length and weight have some association. They are not independent of each other. When a fish is longer, it's likely to be also heavier, right? But with naïve Bayes, we are being naive by assuming that length and weight are independent from each other. So this is a very strong assumption, and because of that, it's going to give us a very simple model. So it's a simple model that doesn't suffer from curse of dimensionality. Actually, this one, when the number of features exceeds some threshold, maybe 4 or 5 features, it needs to calculate some covariance matrix which is 5 by 5. So when P is 5, it needs to calculate some covariance matrix which is 5 by 5. And that's still okay. But when P is 10, it will be 10 by 10 matrix for every single class. So there will be a lot of calculations needed. And also for this one, it's the same situation. We have some covariance matrix which is P by P. But in naïve Bayes, this conditional independence, so this is the covariance matrix. For those of you who had APS 1070 with me, the covariance matrix will be represented with sigma. So these 2 methods need to compute entries of this sigma. But with naïve Bayes, we still have this P by P or 5 by 5 matrix, but we just assume that there's no correlation or there's no covariance between different variables. Therefore, all these entries will be 0. We just need to estimate variance of feature 1, variance of feature 2, all the way to variance of feature P. So there are only P estimates needed for naïve Bayes. While in here, there are P squared estimates needed. So naïve Bayes, because of this, is not going to suffer from curse of dimensionality. So these classifiers are generally going to do a good job for they're going to do a good job for this, for predicting the more likely class. But for predicting the probabilities, they are not that good, actually. So, these are ideas maybe from more than 50 years ago. So later in the course, we're going to learn about more advanced classification algorithms, like support vector machines, which are going to be more powerful for this part. Because this is the difficult task. This one is not really that difficult. For someone who has done some fishing, they can immediately say whether a 100-centimeter fish would be a salmon, not a tuna. But if we ask them, what's the probability that this is salmon, give me a number between 0 and 1. That's a more difficult task. And for that, we need more advanced models. So in terms of curse of dimensionality, logistic regression also is not scalable to large features. So if you have, let's say, 200 or 1,000 features, even logistic regression is difficult to run, to fit. Then we need the idea of regularized fitting, which we're going to learn. LDA definitely fails for 100 features. QDA fails for 100 features. Naive Bayes doesn't fail for 100 features, but it's pretty much only useful for predicting the class, not predicting the probabilities. All right, there was a question.
Yeah, you kind of answered. I was going to say, when would we ever use naive Bayes given that data set?
Yeah, naive Bayes when we only care about whether a transaction is fraudulent or valid, which is not that often. Like if you work, if you want to design some model for a bank, detecting whether a transaction is fraudulent or valid is not, it's needed, but it's not all that the bank needs, because maybe you use some threshold and you say, all right, whenever this estimate that I get, this p hat is larger than 0.9, we will just flag it as fraudulent, right? And don't let it, continue. We stop it. But for the sake of, let's say, regulations, if the bank is supposed to later, file a report or something or investigate what was going on, this is not sufficient, because there might be many transactions that pass this, and many of them are just false flags. Many of them are just type 1 error. Many of them are the actual credit card holder who happens to have a trip to Albany and use their credit card. There's nothing wrong with that. What the bank needs on top of the classes would be the predicted values, the probability, the estimated probability that the transaction is fraudulent, so that maybe for another transaction we get this, for another one we get 0.95. Now, if the bank is supposed to spend hours investigating and writing a report or something for these transactions, they want to start with this rather than with this, because probably there will be many situations when we get this and just sends a push notification to the smartphone of the credit card user. But this is a big deal. This could be something really unexpected, maybe something even more unexpected than, let's say, some Canadian credit card holder being in Albany and using their credit card. I'm just giving the example of Albany because I have a friend who works on this topic, and he told me about situations like this, the false flag of credit card transactions that they get. So that's why predicting these probabilities are more challenging and more essential in applications of machine learning. Predicting classes, we just need to compare these two values and say, all right, we just select the value that is higher. That's it. All right, let's take another break, and then we will continue.